Chemical reactions can either give off or require energy. Now, typically when we talk about that energy, we're talking about either light or heat. And they can either give this off or they can require it in order for the reaction to occur. Now, those reactions that give off or require heat. And this study is called thermochemistry. Now, we won't cover too much of the view of energy from a physics perspective, and some of you may be more familiar with that perspective. I'm just going to gloss over that a little bit with this discussion. So, the concepts of energy is defined as the capacity to supply heat or do work. Now, work is abbreviated with a W. That W looks a little funny. There's nothing funny about the W. It's just a W. That's a physics term. Work is a physics term. We can look at work as the process of causing matter to move against an opposing force. Now, you've likely encountered the terms potential and kinetic energy. Remember, we're going to be looking at this through the lens of chemistry. So potential energy is positional or compositional energy, where kinetic energy is movement. So when we talk about chemicals, chemicals have compositional chemistry. So they do have some potential chemistry. When they're warm, and warm is a relative term, when they're warm, the molecules or the atoms are in motion. So they also have kinetic energy. Now we're going to discuss the thermal energy, and that's where the warm is going to come into play. So thermal energy is a kinetic energy. It is an energy of movement, and it relates to motion, and we measure it with temperature. Now, you've come across temperature before. You've been recording temperature in your laboratory, and if you have a thermometer that is graduated to the nearest degree Celsius, then you know you need to read it to the nearest tenth of a degree Celsius. I don't think I can repeat that enough. Now, when a compound is warm, and I put that in quotes because it is relative, when a compound is warm, there is movement of the molecules and the atoms. When it is cold, again, that's a relative term, there is much less movement. So hot, warm, cold, again, relative terms. They are not specifically defined because it depends on the compound itself. Now, the term heat is one that we will be using here in chemistry, and heat is abbreviated with a Q, a lowercase q, and that's the transfer of thermal energy from two bodies at different temperatures. Now, heat always transfers from the warmer body to the colder body. Matter can absorb or it can release heat. When we absorb heat, we call that an endothermic process. That's something that's going to feel cold to the touch. When matter releases heat, that's called an exothermic process. Exo is outside, endo is inside. So when we release, we have an exothermic process, and that will feel warm to our touch. We measure this thermal energy in calories. Now, we've likely heard of the calorie before. I'm specifically talking about a lowercase c calorie, and that's different from a nutritional calorie, which because a capital C calorie, the nutritional calorie, is actually a kilo energy calorie. So be careful with the nutritional calories versus the energetic calories. The SI unit of heat, work, and energy is called the joule. Joule is abbreviated with a capital J because it's named after a scientist. So the joule is the energy used when a force of 1 Newton, here's a little bit of the physics. When a force of 1 Newton moves an object 1 meter. So 1 joule is 1 Newton meter, which also happens to be 1 kilogram meter squared second squared. Of the things you need to know that 1 joule is a kilogram meter squared second squared. That could come in handy later. The joule also relates to the calorie. So 1 calorie is equivalent to 4.184 joules. This is going to be the most important of the unit conversions for this particular video. Now, the heat capacity is abbreviated with a capital C. So the heat capacity of matter is the heat, Q, that is either absorbed or released when there is a temperature change. Now, that temperature change is shown with a delta T. Delta means change. So when there is a temperature change of 1 degree Celsius or 1 degree Kelvin, now you can use Celsius or Kelvin here because we are subtracting them, and the degree measurements are the same. They're the same difference. That's awkward, but one difference of a degree Celsius is the same as one difference of a degree Kelvin. So heat capacity is equal, which is C, is equal to the heat, Q, divided by the change in temperature. Now, this is determined by the type and the amount of substances that would either absorb or release the heat. This is an extensive property. Remember, an extensive property is proportional to the amount of substance that we have. For example, if we have 2 pans, we have a small pan and a large pan, and we find that the small pan is going to take 18,140 joules in order to change temperature of 50 degrees Celsius. Then we can find the heat capacity by taking the heat and dividing it by the change in temperature to get 363 joules per degree Celsius. So that's how much energy is required to change this mass, this matter, by 1 degree Celsius. So we have a large pan as well. And that large pan takes 90,700 joules in order to change the same amount of temperature, 50 degrees C. And we can calculate that it takes 1,184 joules per degree Celsius, and go with the sig figs here, just roll with it for now. But 1,814 joules per degree Celsius in order to, 1,814 joules, there it is, in order to change 1 degree Celsius. So you see, the smaller the mass, the small pan made out of the same material as the large pan, the smaller the heat capacity. The larger the mass, the larger the heat capacity when we're talking about the same material. So in contrast, we also have what is called the specific heat capacity. Now, the specific heat capacity is a lowercase c, and it's going to be similar with the Q over the delta T, but then we also have a mass term, and I'm going to put that mass term first just to make sure that it's not lost. We also have this mass term. So when we have a specific heat capacity, this is an intensive property, and we take into account the mass of the substance that we have. And let me show you here. So if we have our small, so if I'm finding the lowercase c of the small and the large, what I found was, or what I had was 18,140 joules for 50 degrees Celsius. And I'm going to tell you that the mass of the small pan was 808 grams. Now, for the large pan, we required 90,700 joules and to change the temperature 50 degrees. And the large pan has a mass of 4,040 grams. So when I perform this arithmetic, 18,140 divided by the product of 808 and 50, I get a lowercase c, or a specific heat capacity, of 0.449 joules per gram degree Celsius. So it takes 0.449 joules in order to raise 1 gram of substance 1 degree Celsius. For the large heat capacity, again 90,700 joules divided by the product of 4,040 and 50, I get 0.449 joules per gram degree Celsius. And since I told you these were they were made up of the same compounds, made up of the same material, having the same specific heat capacity is expected. Now, if we know the mass and the specific heat, we can rearrange and find Q. So what I had was the lowercase c, the specific heat capacity, is equal to Qm delta T. Now I can rearrange this so that Q equals the specific heat times the mass times the change in temperature. This is the form you're more likely to see. Remember that the change in temperature, delta T, is going to be the final minus initial. Now, the specific heat of water is something you're going to have to memorize. So the specific heat of water is 4.184 joules per gram degree Celsius. Notice how this specific heat capacity is also a calorie. So the specific heat of water is 1.00 calories per gram degree Celsius. So if you can remember these things, then the conversion should be simple. So how would we work this? Well, if we have a substance and we have 8.0 times 10 squared grams, so 800 grams just with appropriate significant figures of water, and we raise the temperature from 21 degrees Celsius to 85 degrees Celsius. So this is our T initial, this is our T final. How much energy, how much heat, because this is heat, how much heat did the water absorb? Well, we start with our equation. Q equals Cm delta T. C for water is 4.184 joules per gram delta C. Now, if you can't remember this equation, the units should lead you to the answer because our heat will be in joules. So we need to multiply it by something to get rid of the grams and the temperature, the degree Celsius. So I multiply it by my mass, 800 grams. And actually that's incorrect with the significant digits, but we will just know from above, 800 grams times the change in temperature. So I take my T final, which is 85, and subtract my T initial, 21. And those are degrees Celsius. So when I perform this calculation, I get 220, and that's joules. So 214,220 joules. This is a case where it would be better to report kilojoules. Now remember the prefix kilo means 1,000. So there are 1,000 joules in 1 kilojoule. So I move my decimal place over 3 and I get 214.220 joules. But looking up here, I had 2 significant digits here and I have 2 significant digits here. So I would say this would be 210 kilojoules is what we would report. Similarly, we can calculate specific heat capacity if we have the heat, mass, and temperatures. So again, using my equation, Q equals C times M times delta T. If we have a sample that has a mass of 348 grams, and that absorbs 6.646 kilojoules of heat. If we start, so our TI, at 22.4 degrees Celsius and end, so our TF, at 43.6 degrees Celsius, what is the specific heat of this substance? Well, I'm going to use this equation and I'm going to fill in what I know. So the Q is 6.646 kilojoules. We need to convert that into joules. So I will have 6646 capital J joules. C is what I'm looking for. The mass is 348 grams. And the change in temperature is going to be the final temperature minus the initial temperature. So 6646 joules equals C times 348 times 21.2. So I multiply these two items together. 7377.6 is what I get. Now I have to watch my significant digits here. I only have 3 significant digits here and here. So I'm going to just underline that. That's what I'm going to focus on, are those 3 digits, even though I'm going to leave them in the calculator in order to avoid rounding error. So I divide both sides by this number that was still in my calculator. So C equals 0.900. Now this, and that's my 3 significant digits. There were a couple others after that, but these are my 3 significant digits. Now this may be aluminum. Aluminum has a specific heat capacity of 0.897 joules per gram degree Celsius. And I know that because it's in a table in the e-text in your classroom. Now in the laboratory, we can measure the amount of heat in a process, and this is specifically a chemical reaction or a heat transfer from a hot metal to a solution. And this is called calorimetry. Now in a laboratory, we have what's called a bomb calorimeter, and we literally blow up a sample, hence the bomb. It's a fixed volume. What we're talking about here is going to be something more that you could do at home with your lab kit. So we need to define what is a system and what are the surroundings. So the system is the substance undergoing the change, whether that's chemical or physical. The surroundings are the other parts that provide heat to the system or absorb heat from the system. So most of the time in our lab kits, we end up with these styrofoam cups to act as a calorimeter. And you end up putting 2 styrofoam cups together, and that is your surroundings. So your system ends up being a solution that you're taking a temperature of, or it's a piece of metal that is giving off its heat to the liquid, which is usually water. So this is a calorimeter. So in calorimetry, we have some sign conventions. In calorimetry, Q, which is the heat, is negative when you have an exothermic system. So that means the system gives off heat. In calorimetry, Q is positive when you have an endothermic system. That means the system is absorbing heat from the surroundings. Now, heat will always flow from warm to cool. So your warmer substance will give off its heat into the cooler substance. Now the Q, or the heat of the system, plus the Q of the surroundings, so the heat of the surroundings, is defined as 0. That means the heat of the system is equal to the negative heat of the surroundings. We can use this with some problem solving. For example, if we have a hot piece of metal, and that hot piece of metal has a mass of 360 grams, it's submerged in 425 milliliters of water, and that starts at a temperature of 24.0 degrees Celsius. So this is my TI, here's my M, I already did that. So you see how this is going to shake out immediately. So the final water temperature is 42.7 degrees Celsius, what was the initial temperature of the metal? Well, the C of the metal, so the heat capacity of the metal, is 0.449 joules per gram degrees Celsius. That's what we calculated in our pan example at the beginning. Now the Q of the metal, which is the system, is going to be equal to the negative Q of the water, which in this case is the surroundings. Now we don't know the mass of the water, but the density of water is assumed to be 1.0 grams per milliliter. That's generally correct when you're looking at about room temperature. So we're going to go with 1 gram is 1 milliliter. Now I have the Q of the metal is equal to the negative Q of the water. So I can fill in my equation. So the M of the metal times the C of the metal times the delta T of the metal is equal to the negative M of the water times the C of the water times the delta T of the water. And then we fill in what we know. So we know the mass of the metal is 360 grams for 9. And the delta T, I'm just going to leave this as delta T right now, even though we do have the final temperature of the metal, because the final temperature of the metal is going to be the final temperature of the water. Now that we have the mass of the water if we convert our milliliters into grams. And since we're defining that at 1 gram per milliliter, we're going to call that 425 grams of water. Specific heat of water is something you're going to need to remember, 4.184 joules, grams, degrees Celsius. And then the delta T. Now delta T of the water is going to be equal to the final temperature minus the initial temperature. It looks like I'm about to run out the page, so I'll put my 24 down here. So that difference is 18.7. So that's just what I'm going to write down here, 18.7. So now I perform the calculation. When I calculate all of this in my calculator, I'm going to give you way too many digits. I want you to leave the digits to avoid rounding error. So 33252.34, and that's joules. And that's going to be equal to 161.64 times my delta T. And that's equal to this business. I'm going to divide both sides by 161.64, so I have my delta T, or my delta T is equal to a negative 205.7185, and then there's a whole bunch of other digits. Again, leave it in your calculator. Now, the delta T of the metal is going to be the final temperature minus the initial temperature, which I don't know. And that's equal to negative 205.7185 and the other digits that are still in my calculator. So now I subtract 42.7 from both sides and get a negative 248.4185, etc., etc., etc. Multiply through by -1 to get rid of my negative, and my initial temperature was 248 degrees Celsius. So similarly, we can use this kind of approach in order to find other missing variables as well. Then we need to remember that the Q of the reaction, which is the system, is equal to the negative Q of the solution, which is the surroundings. So if we have 50 milliliters of a 0.01 molar HCl solution, some of the labs will have you measuring the heat of a chemical reaction. And here we're going to show an acid-base neutralization. So I have 50 milliliters of a 0.01 capital M molar HCl, and I have 50 milliliters of a 0.10 molar NaOH. And that is at, so my TI is 22.0 degrees Celsius, and that's for both of my solutions here. And we put that in a calorimeter, and that reaches, so a final temperature, 28.9 degrees Celsius. What's the heat produced by this reaction? Well, here is my reaction. Here is my solution. So when I mix these two compounds together, when I mix these two liquids together, that is my solution. So the Q of the solution is going to be the C of the solution times the mass of the solution times the change in temperature of the solution. Now, when you're working with an aqueous solution like this, so these solutions are aqueous, they are in water, then we take and we approximate the density at 1 gram per milliliter. So unless you're told differently, the density should be 1 gram per milliliter. It's possible in your lab you have to measure your own density. That's okay too. So the C of the solution, the specific heat capacity, because we're working with aqueous solutions, is going to be 4.184 joules per gram degrees Celsius, multiplied by the mass of the solution. Now the solution is when we add these two items together. So it's 100 grams for my solution. And then we multiply that by the change in temperature. Now the delta T of the solution is going to be 28.9 minus 22.0. So the delta T here is 6.9 degrees Celsius. So when I multiply all of these things together, I get 2886.96 joules. I would report that in kilojoules because that would be easier. So I move this over 3, 1, 2, 3, and I get 2.89 kilojoules for the heat of my solution. But remember, the heat of the reaction is going to be the negative heat of the solution. So the Q of my reaction is going to be the negative heat of the solution. So the negative number indicates that this is an exothermic reaction. It gives off heat.